Over to you, Tammo.
Okay, thanks, David. Well, welcome everybody to this webinar on the CircAdapt lump parameter model of the cardiovascular system. As you can see, my email address is written in the right lower button. So if you have any questions related to this webinar, you can address them either by email or call me at my desk, but that will be more difficult. So what we are going to talk about is CircAdapt, which is a closed loop and a multi-skill cardiovascular system model. But it is lumped, and it is lumped at different levels. And starting at the system level, we started the other way around. The arrow is from the left lower part to the right upper corner. So from that is the reductionistic approach, that you start with very minute things, and then you construct more. But we started from the other way around. We first looked at the whole system, and then moved downwards towards ion channels at cellular levels. So we started with the system, the original CircAdapt description, which was in 2005 by Arts, me, Peter Bovendit, and Princeton. And then, we at that very moment we were only able to mimic the hemodynamics and mechanics of two spheres of the ventricles in two spheres of the atria connected to a couple of tubes. And then in 2008, we started out that we wanted to construct a model which could be used to estimate right ventricular pressure. And in order to do so, we had to adjust our original two-sphere models into a double bubble, a soap bell model. And that was the CircAdapt TriSec model, which has been published in 2009 and further on 2012. And then even more, we wanted to have dyssynchrony and local tissue properties. And that's when the CircAdapt MultiPatch model came in. And then we changed the heuristic approach to the sarcomere mechanics towards a more physiological, physics-driven action contraction model, which is written down in Dupuy et al. In PLOS Computational Biology. And I will guide you through these changes and through the various modules. And the primary goals of our model were that we would like to have a real-time simulation tool on the human cardiovascular system dynamics that can be used both by basic researchers and students in biomedical engineering and medicine. But it's not only a research tool, but also an educational tool. And with that respect, I would like to draw your attention to www.circadapt.org, where you can find all the documentation related to CircAdapt, but where you can also download an educational version of the CircAdapt model as it was in 2012, not with the latest editions. We're working on that, but it's not available yet in the educational version. So, and finally, of course, we would also like to have a model that can be used maybe by clinicians as a clinical support tool. But in order to be able to do so, there are some requirements, and that is that it should be primarily based on physical and physiological principles, that it should be physiologically accurate. That's where we put a lot of emphasis on, and we always try to compare our results with independently derived physiological or clinical measurements in order to assess our approach. And we want to have a modular structure because that allows modification by, it's written down here, teacher and student, but we can also easily, as a researcher, modify the structure of the model if it is modular. And that's very handy. I will show you. And we would like to have a maximum validity range with a minimum number of parameters. It is, like Kipling has said, with 4 parameters. I can draw an elephant and give me 5 parameters, and I can jiggle his tail. So that's why, you know, the more parameters you have, the more likely you are to be able to simulate something that resembles in appearance the physiological reality, but you don't know whether you really got the essence of the physiological reality. And that's why we would like to have, you know, a minimum amount that is needed to visualize physiology. Now, the modules that we use are the various ones. And you can see the various elements of the cardiovascular system, from chambers, which is here the trisect model for the left and the right ventricle, and here this one for the atria. And in circle, the numbers, they relate to the number of state variables that are involved with these modules itself. Now, then we have valves, which are governed by inertia and the Bernoulli effect. Then we have, of course, vessels that connect the various parts. We have the arteriovenous network, which consists of resistances and compliances. And then we have also bags that is a pressure around a group of modules, and which has just a passive properties, volume pressure related. And those bags, for example, can be the pericardium, but it can also be the pleura, the thorax, whatever you can envision as a entity that is encapsulating certain aspects of the cardiovascular system. And then these modules need to be connected, and that has been done by nodes. Now, if you have now these kind of modules, you can see that it is easy to have the basic aspects of the cardiovascular system, in which you have a systemic circulation and a pulmonary circulation. But the modules allow us also that a valve is not only a valve in between the right atrium and the right ventricle, but you can also make, of course, a connection between the right ventricle and the left ventricle, which mimics the VSD. And the basic principles of a valve also apply to holes within a septum, either the VSD, ventricular septum defect, or an atrial septum defect between the right atrium and the left atrium. But we can also connect the pulmonary artery towards the aorta by means of the ductus arteriosus. So with these kind of modules, you can see that you can construct any kind of circulation which you can think of. For example, a tricuspid atresia, in which there is no valve between the right atrium and the right ventricle, can be constructed, because in those cases there is always, or hardly always, an ASD that allows the blood from the right atrium to pass to the left atrium, then to the left ventricle, then by means of a particular septal defect towards the right ventricle, and then into the pulmonary artery. But in case there is no right ventricle at all, then still it is possible to arrive at the pulmonary circulation by means of the left atrium, the left ventricle, then going into the aorta, and then by means of an open ductus arteriosus, and then go into the pulmonary artery. So this plumbing system is very, very versatile when it comes to congenital heart diseases, or the way the cardiovascular system is structured. Now, the system itself consists of ODEs and ordinary differential equations with 32 state variables in this form of CircAdapt that I show you right now. Of course, if you increase the amount of modules or the amount of arterial venous system, then you will have more state variables. But this is the basic form. Then you have a 4-chamber heart with an interventricular septum. You have the interventricular mechanical and hemodynamic interaction, because it's not only, here are the connection points between the right and the left ventricle, but also the pericard encapsulates the right ventricle, and that gives also rise to mechanical interaction. And then, of course, the output of the right ventricle will arrive eventually at the left ventricle, which also gives an interaction, but that is all within the model. Then we have the atrioventricular and ventricular-arterial hemodynamic interactions. We have flows through valves and vessels, and we have a closed loop system with two peripheral vascular beds, the pulmonary and a systemic circulation. Then the pericardium around the heart, which was the back, as I told you before. And then we have the flows again with three potential shunts, the atrial defect, the ventricular septal defect, and the patent ductus arteriosus. So it's very important that this original program, but also what further on was constructed, would never have been possible were not by the Theo Arts worked for years on this project. Within our, he is an emeritus professor right now, but he still comes in every week, and we have numerous discussions on these items, and he is of tremendous value to us. Now we will go more into detail about the modules, and for the chamber, so the contractile element, it's very important that we have the principle of that no energy is lost, so conservation of energy work. And that means that the mechanical work in the walls, the sum of that equals the summed pump work. As you might know, is that the area of a pressure volume loop is indicative of the amount of external work that is performed by a ventricle. But in general, it is also that if you have a loop of myofiber strain versus myofiber stress, then that area is also indicative of the amount of work performed by that myofiber per volume. So if you then sum up every individual small volume of the walls, the work that has been performed on a local level by that, if you sum that, it should finally be the same as the summed pump work. Now, if you know that, then you see in the top there that the work is equal to fiber stress times strain, the difference in strain. But that is also valid for tension times the change in area size. And that holds then from the myofiber towards the wall. Now, tension times area also equals pressure times the difference in volume. So you can derive from a myofiber towards the wall, towards the chamber, either for one wall, one cavity, like the atrium, or a trisac system with 3 walls and 2 cavities, the ventricles. Now, you should realize that because this is a trisac model, the work that has been performed by tissue in the right ventricular free wall is not only used for pump work of the right ventricle, but can also be used for the pump work of the left ventricle. So the sum of the mechanical work in the walls, you should sum up every wall. Sum of work in this wall and that wall and this wall, the left ventricular free wall, those together are equal to the sum work of the left ventricular pressure volume loop and the right ventricular pressure volume loop. Important to keep in mind. Now, for the myofiber, we use the modified 3-element Hill model, which has the length-dependent activation and the force-velocity relationship. And I refer to physiology books for you to read on that item. Now, these sarcomere mechanics within our model, they are based on the one fiber model. And what we assume is that if you have a fiber and you wrap it around and around and around and around and around and around, then finally you can have, you know, a wall which consists of one fiber, and you can reduce the amount of mathematics and mechanics to only solve for that specific one fiber. There is a seminal paper on that. It was in a 1998 paper by Theo Arts in the Biophysical Journal, which you see here down below. And if you want to know more of the background for that, I really strongly advise you to read that paper. What it does is that you have, you know, as a series elastical element and a contractile element in series, and yet you have the parallel passive element. And those three elements together, they are used in order to calculate or estimate the sarcomere mechanics. Myofiber stress in this model is a function of sarcomere length and time. So the physiological properties that were used is that shortening velocity increases with applied external force, and that contractility increases with sarcomere length. And finally, that activation duration increases with sarcomere length. Now, if you want to go from the sarcomere towards the chambers, what we do is that we have to keep in mind that the myofiber stress can be transferred to tension in the wall by using that Laplace's law that the transmural pressure equals twice the tension, the wall tension times the curvature. And to come from myofiber stress towards wall tension, we need assumptions that walls are spherical caps, and that wall tension is homogeneous within each wall, and that wall tension acts in the middle of the wall. And finally, that the fiber direction is parallel to the wall surface. That you will get automatically when you wrap, of course, the fibers. But we explicitly state that fiber direction is parallel to the wall surface in our assumptions, because as a second order effect, it is not parallel, of course. There's always a transmural fiber angle, because fibers also need to go from the endocard towards the epicard, though in a very gradual way, but finally there should be some transmural course. Now, this slide shows you very basically now what will happen. If you have blood flow, in this case then from, for example, the right atrium towards the right ventricle, the volume of a chamber will change. And the chamber is a cavity surrounded by walls. And not only that volume then will change, but also finally the length of the myofibers will change. Or the other way around, if you know the length of the myofibers, you know the cavity volume, and you could deduce how much flow there would have been. And these relations are important, as I will show you in the later part of this slide. A blood flow, as said, will change cavity volume. Cavity volume will have its impact on wall area and the curvature, and that will have its impact on myofiber strain. Now, using that three-element sarcomere model, you can calculate for myofiber the myofiber stress. And then you go to wall tension, as said before, by means of that they are equal. And then, if you know the wall tension, and for well, this is maybe a little bit too far, but in order to do so, we also need a force equilibrium at the attachment points of the left ventricular to the right ventricular spheres. But if you know wall tension, you can again calculate wall area and curvature, but also you can estimate cavity pressure because you know the relation by means of the Laplace's law between wall tension and cavity pressure. And then if you have then the cavity pressure updated, you can again estimate how much blood flow would have been made by means of that. And that makes that the circle closes. And you can go from volume towards pressure, and then you go to the next time step. Again, importantly, the amount of work remains equal pressure times the volume change, tension times the area, or the summed work of the fiber stress, fiber strain. And having these constraints, you can calculate it by means of this circular wave from cavity volume towards myofiber strain, myofiber stress towards cavity pressure, and coming back again. Now, how has this been used? I will show you here an example of an heart on the left side, which is normal electrical conduction. That means that the origin of the activation is in the sinoatrial node. From there, it spreads around the left and the right atrium, comes at the AV node, and then very fast across the Purkinje system, and then spreads synchronously, more or less, across the left and right ventricle. But in case of a left bundle branch block, when there is a blockade here at this part, then the left ventricle is not activated by means of the Purkinje system, but by means of myocardial conduction from the right to the left ventricle. That gives rise to a very asynchronous activation of the left ventricle. But that will also have its impact on mechanics. Now, if you look here at the results of our CircAdapt model, you can see what we were able to do with our very simple tri-sec model. You have here in green the left ventricle, in blue the right ventricle, and here in the plots on the y-axis, on the top plot, you have the pressures of the left and the right ventricle, then the volumes of the left and the right ventricle, and then the flow from the left ventricle towards the aortic valve, or from the right ventricle towards the pulmonary valve, and then you have here the tricuspid valve and the mitral valve flow. What you see is this is the E wave, the early filling of the left ventricle, and the A wave, due to the contraction of the atria, is here. So it is a double-headed mitral valve pattern, but it is splitted amongst to the left and to the right for visual purposes. Now, from these pressure and volume curves, you can of course derive pressure volume loops, which you see here, and the work of the left ventricle here is the area of that pressure volume loop, and of the right ventricle, of course, of the blue loop. And you see that the external work of the left ventricle is approximately 4 times more than of the right ventricle, not because stroke volume is different, but because the developed pressure is different. Now, if you now look at local tissue mechanics, and now we focus only on the left ventricle with here the septum and the in red and the left ventricular free wall in black, you see that the myofiber stress of those walls follows more or less closely each other, and also the myofiber strain clearly resembles that of volume change because they're one-to-one related. What we also can do is that we look at how the diameter changed of the left ventricle, and how the wall thickness of the septum and the free wall changed during the cardiac cycle. and this more or less resembles an M mode, an ultrasound M mode of the left ventricle. The myofiber strain, myofiber stress curves of loops here are again, a measure of the local work performed by the septum or the free wall, and you have to multiply this by the size, the mass of the free wall or the septum, in order to derive to the total work of that specific part of the ventricles. It's myofiber work per unit tissue. Now, if you have simultaneous activation and no delay, the left ventricular free wall and the septum more or less have the same amount of work per unit tissue. But if you now change the activation time of the free wall with a 10 milliseconds delay, you clearly see that those curves are not, similar anymore. The red one, the septum, you see that there is an early shortening, which is here, that early shortening, whereas the black one is later activated and shortens later in time. So the septal myofiber strain stress loop is squeezed, whereas the free wall is a little bit, blown up. And this effect becomes even more with more delay, 20 milliseconds delay, or 30 milliseconds delay, 40 milliseconds delay. And then you can even have a figure of 8 loop in which there is negative work. That it means that there is work performed on the free wall. These results, they are from our model, but if you compare those to results of animal experiments on dogs, you clearly see that though it is a very simple model, only with 3 segments for the ventricles, clearly you get results that resemble what has been measured in dogs with an acute left bundle branch block. Here in the dashed line is the septum, which shows that a very early shortening, a negative strain, a little bit lengthening, again shortening later on. And this pattern you see clearly in our simulation results. And you also clearly see that as we saw in our simulation, that the free wall was extended and then had a more vigorous shortening. That is also the case in the dogs with the left bundle branch block. That shows that the lateral wall has, primarily a first extension and then an enhanced shortening. But also the myofiber stress strain loops, they also did it in dogs, though you cannot measure a really stress in vivo or in the experiment. So that's why they took a proxy for that and used just the measured and estimated left ventricular pressure. And then you see that if you do pressure, which is a proxy for stress, you put that against the strain, that you get clearly in dogs as well, figure of 8 loops with negative work and for the septum, whereas the left ventricular lateral wall is blown up and has to perform more work. So even with the trisect, only 3 segments, we were able to get to these results, which, is very encouraging. But left bundle branch block is not, this is a first order approximation if you only say that you have a septum which is early activated and a free wall what is late activated. So we wanted to incorporate heterogeneities in the CircAdapt model too. And for that we made additional assumptions. We assumed that the wall contains of pieces, patches, that act in series, and that every patch has the same kind of it's a module. Now the module is patch, And what we assumed is that wall tension is similar for each patch. You know, they are in series, so they feel the same kind of forces wherever they are. And therefore, location of the patch doesn't matter. It doesn't matter whether an early activated patch in our model is in the beginning of the chain or at the end of the chain or just in the middle. We also had to assume, which is clearly not really true in reality, that wall curvature is similar for each patch. But we had to do so, otherwise we couldn't solve our equation. The effect of this assumption, and it is, a little bit of a violation of reality, I think that is minor as compared to the values of the results. And then what we also then got is that the properties of patches can differ. So you see that the transmural of the wall tension is everywhere the same, the curvature is everywhere the same, but the tissue properties, the activation time or the passive properties or contractility, they can change per patch. And location doesn't matter, so it's not a matter of it's blue-red is the same as red-blue. And now you see here for the left ventricle number of patches, septum and number of patches, and you can of course not only change the tissue properties with respect to the passive behavior or the active behavior, but you can also change the activation time. And now you can see here, for example, that if you have right atrial pacing, then you get more or less a synchronous activation of your ventricles, which is not completely synchronous. So hence you have activated with after your atrial activation, you have an early activated and a later activated area, but the differences between them are just in the order of 20 milliseconds. Again, this is not a local situation. This patch having 20 milliseconds delay could have easily been there. It doesn't matter as long as it is within the same segment of the tri-segment. But if so, then location doesn't matter within that segment. Now, right ventricular apex pacing, we mimic that by having a very asynchronous activation of the left ventricle and also a bit of the right ventricle, because the right ventricle, if you pace it at the apex, parts at the right ventricular outflow tract free wall will be later activated, of course, than if you would have a synchronous activation by means of the Purkinje system. But for the left ventricle, it's even more debilitating if you have right ventricular apex pacing, because you can get activation which are up to 100 milliseconds delayed with respect to the pacing side. And you can also do the other way around, that you have left ventricular base pacing, which gives rise to a very late activation of the septum and the right ventricle. Now, we compared the results of these kind of simulations to paced canine experiments that were old experiments done by Professor Prinsen from Maastricht, as well as by me in my PhD period with him. And here it's a very busy slide, but I will guide you through. On the left side, you see canine experiments. Sorry, at the top you see the results of canine experiments, and in this case, it is it's like a circle around the left ventricle, and you see here, the septum. Then you see curves related to the anterior aspect of the left ventricle, then to the lateral, then to the posterior part, and then to the septum. And with right atrial pacing, you see that the strain of the various locations, at the various locations within the left ventricle, are more or less homogeneous. Fiber stress also is more or less homogeneous pattern for the same locations in the left ventricle as during right atrial pacing. Now, CircAdapt simulation is at the bottom. There you see clearly that the strain pattern during the ejection phase, which here was only the ejection phase, that the strain pattern in the simulation during ejection phase are also very similar for any location, and they are very similar to the canine experiments as well as the strain, the stress curves of the various locations. Now, if you now go to right ventricular apex pacing, what you see is that, and the pacing side is for right ventricular apex, the septum is very early activated with respect to the lateral free wall. Again, you saw in the dog experiments an early shortening of the septum and then a lengthening, whereas the free wall had an extension, was lengthened, and then had a more vigorous shortening. But now look at the strain curves of the CircAdapt simulation. Well, aren't they strikingly similar? So we are very encouraged that our MultiPatch approach is valid in order to simulate the results, and that can be compared to animal experiments. And not only for the strain, but also for the stress, which you can see here, that they also resemble the ones that were estimated in the animal experiments. And even more so with the left ventricular free wall pacing. Now the pacing side is in the mid of the left ventricular free wall, giving rise to early shortening there, and then a lengthening during the ejection phase, and a more vigorous shortening at the septum. Well, if you compare that to the animal experiments, well, again, strikingly similar, not only for the strains, but also for the stresses. So this is something that we used these kinds of simulations we do use in order to find a proper pacing setting for patients when they got cardiac resynchronization therapy, and you try to get the hearts as synchronous as possible, but still have to take into account the hemodynamics of the right and the left ventricle as well. And our modeling approach allows us to do so. Now we have to change topics, and we go to the valve. The valve module has a couple of assumptions, namely unsteady, incompressible, and non-viscous laminar flow. We assume no effect of gravity, and most importantly, maybe no regain in pressure. That means that we do have the Bernoulli losses. If you get an increased velocity across, for example, a stenotic valve, then or a valve at all, then we assume that afterwards the increased velocity there is a loss of pressure due to the fact that velocity, when you reduce it again, when you come in the more distal area, so in this part, then the reduction in flow velocity will not be converted into hydrostatic pressure. Well, I think it goes into too much detail, but you will have the slides afterwards, and you can have a look at them and then come to me later on. But there is too much detail if we talk about how we implemented inertia, that we had to assume a certain length of the valve as well. So I leave it by this for the valve, but for the interested reader, there is more on this topic in slides that we show with respect to what stenosis is, and that I will show you later on in this presentation, and there you find the literature reference towards this item. Now, well, actually, this is already the slide with respect to aortic regurgitation, because that is another application how we could use the model. It was a trisect model with the valvular module, and we tried to estimate how diagnostic measures of AR, aortic regurgitation severity, depend on the left ventricular aortic stiffness, because what they normally do is they just measure how the velocity across a stenosis is, or how the regurgitant flow pattern is, but then people in real life cannot take into account, because you don't have measures of that, they cannot take into account what the aortic stiffness would do, or left ventricular stiffness on this subject. So we thought we might use the model in order to estimate the effect of aortic stiffness on the regurgitant flow pattern across the aortic valve, and we do the same so for the influence of left ventricular stiffness. And then we do it with an increasing regurgitant orifice area from no regurg at all to mild to moderate to severe. And what you see here is with an increasing regurgitant orifice area, you see that the slope here of the backward flow, this is the flow velocity across the valve, and this is the backward flow. You see it's a very high flow velocity, because of course the driving forces from the aorta with its diastolic pressure are so high as compared to the left ventricular pressures during diastole, especially in the beginning of diastole, that you get flow velocities of 4 to 5 meters per second. But if the regurg is very mild, then the filling speed of the left ventricle will not be that high, and hence the slope of this regurgitant flow pattern will be not that much. Now you see, if you have an increased regurgitant orifice area, the slope increases, and then with the most severe, the slope is highest. So there is a relation between the slope and the severity of aortic stenosis. But what will happen now if you have a stiffer aorta, or a stiffer left ventricle? Well, this is actually the results of by having a normal left ventricular and a normal aortic stiffness. But what we saw is that if you only use the steepness of the curve as a measure of the regurgitant orifice area, that you are getting into a dangerous situation if you have a stiffer ventricle, because a stiffer ventricle also leads to an increased slope, because the stiffer ventricle will faster reach higher passive pressure volume parts of the relation, and hence higher end diastolic left ventricular pressures, and hence the driving force from the aorta towards the left ventricle will be less, and hence the velocity across the valve will also be less. So it turned out that the slope of the regurgitant velocity is not only dependent on the severity of the aortic stenosis, but also on the severity of left ventricular fibrosis. So you should be aware that the interpretation of signals is not as straightforward as you might think originally. Now, another aspect, what we used for our model is that another aspect of our model is that it also incorporates adaptation, and that's why it's called CircAdapt. The adapt part of the CircAdapt model facilitates the fact that we have less parameters, because instead of approximating or guessing parameters or adding new parameters, you use adaptation processes to derive to parameters. For example, if the load of tissue is higher, then there will be a change of the global shape. There will be mechanosensing. There will be referred to a reference value, and that will change local tissue properties. So the change induces its own effects on the tissue properties, and not only in the vascular part, but also at the chamber part. And this enables us to, for example, if you have a hypertensive state, you go from normal to hypertension. Our model, you can just implement that there will be an increased resistance in the systemic circulation, and you will get hypertension, but then the left ventricle and the right ventricle itself will automatically adapt their tissue properties to the new situation of the hypertension. Whereas, for example, if you have a time-varying elastance, you not only have to adjust the peripheral circulation in order to reach to hypertension, but you also have to change the settings of the parameters yourself for the time-varying elastance model. So we think that this is a very this comes very at hand for modeling purposes of the cardiovascular system. So, in conclusion, CircAdapt is a realistic self-structuring model of circulation dynamics, and, well, at least in our opinion, it is an excellent compromise with a minimum number of parameters, a large validity range, and most importantly, maybe also low calculation effort. In MATLAB, it's in real time, and in C++, it's even much faster than real time. So you can predict what will happen in future right now, you might say so. The applications are education of circulation physiology, patient-specific modeling in the clinic, simulation of pathology and surgical repairs, short and long-term effects, and it's a very, very versatile research tool. As we show you here, this is, for example, the scientific papers, but I did mention only till 2016, not to mention what we did in 2017, 18, and already in 2019. But it shows you a broad application from left heart failure, cardiac resynchronization therapy, right heart failure, pulmonary arterial hypertension, including, for example, the effects of pot shunt versus atrial septectomy. Then we have the arrhythmogenic right ventricular cardiomyopathy, in which we use CircAdapt in order to derive to values that you, by means of looking at the mechanics, you could already predict whether there would be an electrical problem, yes or not. We applied it to valvular heart disease, like the aortic regurgitation. We also do a lot with exercise physiology. So very versatile and a very broad range of application possibilities. This, we think, cannot be performed if there would not be a strong cooperation, a collaboration, integration, and translation between cardiology, physiology, and biomedical engineers. You do need the clinic for getting the patients and the problems. You do need the physiology to do animal experiments and to get a more basic knowledge on it, but the modeling approach is also of impeccable validity and usefulness together with the imaging and experimental approach, and that will together give improved diagnostic and therapeutics. But we in our belief, it is very important that all these parties are involved, because if, from the engineering point of view, you don't take into account the physiology or the cardiology, you might get very beautiful models with beautiful numbers and pictures, etc. But if it does not, you know, uh, it's not correct from a physiological point of view, or it is not that the cardiologist cannot work with it, or cannot provide the data, which is important as an input source for the models, then it's of no use. So a lot of people have to be acknowledged. In the ones that are closely collaborating from other universities, the Utrecht, Washington University in St. Louis, and in Bordeaux. But the main team is, of course, at Maastricht University with Theo Arts as the founding father. And I would like to mention especially Joost Lumens, who is now doing a lot of work with the CircAdapt, and actually the driving force behind that. Having said so, I would like to thank you for your attention. If questions remain, which might be so, because you never can tell within 1 hour the complete story of a modeling process of decades, then I'm more than happy to answer them. Thank you for your attention, and I would now like to turn down the mic to David Jordan again.
Okay, thanks, Mo. That's a really interesting demonstration again and presentation. There's a lot of great stuff in there, a lot of fantastic links for you guys to follow up with. Really big thanks to you all for attending on a Friday afternoon, because I know you're all busy with various things, and so it's great to have you here. We will present a version of this PDF, and it will be available on the website, and at some stage we'll do a small edit on the video and make the video available. So I wish you all an excellent weekend, and thank you and so much.
Okay, thank you very much. Bye-bye.
Bye, Jamal. Thank you so much.